There we go. Okay, so uh, on Tuesdays and Thursdays, I like to talk about the lab that we're going to be doing. And I also like to open it up to questions that you may have, but we're going to go ahead and start with the lab that you're going to be doing, the lab that I technically am assigning today, but and is due next. I'm not sure when it's due. I might change the due date. So we're going to start with the lab, and then I'll open it up to some questions in just a moment. Unless someone has an urgent question that they would like answered, in which case I'll address that. Anyone with an urgent question? Okay, that being asked, let's take a look at the lab. And we're going to be looking at the density lab. So the idea here is I want to help you write this up in your lab notebook and submit the correct information and so forth and so on, so that you can feel comfortable doing that job. I'm going to change my share from me to something far more useful, I hope. And that's going to be my web browser. So this morning, someone was saying that they were having trouble looking at the videos. So in module 1, I'm going to collapse this module 0. In this module 1, they had trouble seeing the videos in at the end here that say module 1 Q&A. These are the Zoom videos. And we figured out that their issue was that they were using the Safari browser and it wasn't working. When I do this in Chrome or when I do this in Firefox, it works. I don't use the Microsoft browser, whatever that one's called, Explorer, I think. So it works in Firefox and it works in Chrome. Okay, that being said, here's the density lab. And hopefully you can see what is written here for the density lab. If you can, just give me a little thumbs up or some sort of signal. I don't care what. Okay, good. Now with 3 of you here, if I get one signal, I'm just going to move on. And your job is, if I'm moving on too fast, you need to give me a signal that says, slow down, Tony. And the best signal is you unmute yourself and go, whoa, Tony, I have a question. Or, whoa, Tony, can you slow down? It won't bother me at all. You might catch me off guard, but I will slow down and address whatever it is you need to have addressed. Fair enough? That's a question. Okay, so let's move on. You can see that I want you to submit with your lab notebook the following sections: title, intro. I'm not going to read through all of these, but we will talk about all of these in just a moment. Submit the following photo, a close-up image of the meniscus in your graduated cylinder. And this is with just the water in it. And make sure that you have the camera at the correct eye height for the meniscus. We talked about that and how you arrange the lines on here so that your camera height is at the right height. And this is just so that I can make sure that you're recording the proper value using your graduated cylinder. And I will figure that if you have that value correct for the water in your graduated cylinder, then you will have it correct for following volumes in your graduated cylinder. And also you want to submit the answers at the end of the lab, or answer the questions and submit answers. We will take a look at that in a moment, but let's take a look first at the title. So for the title, you're just going to call this density. If you want to do something more, you'd call it the density of pennies and dimes. Now for the background here, which you can incorporate into the introduction, I talk about density, how it can be determined. And basically density is mass divided by volume. And you determine the density by getting the mass of an object and you get its volume. 2 ways to get the volume: by water displacement, which is this image right here, and also by geometric shape. And then I talk about coins. They're made out of metals, used to be precious metals. I give you an explanation for the term 2 bits. That'll be 2 bits, cowboy, which is a quarter. I also give you this stupid story about Archimedes, which isn't true, but I just try to make it fun. I mean, chemistry is pretty daunting to some people, so you got to try and make it somewhat relatable. And then I talk about how pennies and dimes are made out of copper and nickel, excuse me, copper and zinc. And I think when you look at a penny, it looks like it's made out of copper. When you look at a dime, therefore, it's made out of zinc. And so that's kind of like a hypothesis for what they're made out of. So our learning objectives don't go in the introduction normally, but this is the stuff we're going to be doing. Materials don't usually go in the introduction. But before we're ready to write what we're going to do in the introduction, let's take a look at the procedure. We're going to get the density of water. So you mash your graduated cylinder while it's empty and dry. Then add about 40 mils of water, then mass it again. One of the things I forget here is I didn't ask you for the volume, but that's all right. I'll add that. Let's go back to here. And you can see how I edit things now. Edit. I saw this new TV program on today. It was from the White House. And there was a person who was talking about what the president was going to be doing today or in the short future. And they started fielding questions. I've never seen anything like that before. At least not in the last 4 years. It was really interesting. It was brief too, and it came from the White House. And I think they called it the White House briefing. Fancy that. Okay, so what was I going to change here? Right here, density of water, mass it, add about, mass the water, and also record, measure, and record the volume. Okay. Apparently I think record is spelled differently than it should be. Oh my goodness, look at all these spelling errors. Okay, so that's the picture you're supposed to take, the volume in milliliters. Okay, so now I'm going to save this, so I need to scroll down. And let's see. Where's my save button? There it is. Okay. All right, so back to this. If you look at the where we were looking at the procedure, mass the graduated cylinder while it's empty, add anywhere around 40 mils of water, mass the graduated cylinder with water, measure and record the volume in milliliters. And you can see that the density, very straightforward. And you'll notice I put these procedural instructions in bullet points. In this particular case, when you're writing out your procedure, can you see where it says, because it is impossible to measure anything exactly and measure the volume of water? Oh, shoot, I already had that. So I can delete my little fourth thing there. Okay. So you don't need to put that because it is impossible. Basically, when you get the density of water, you say mash your graduated cylinder empty, put 40 mils of water in it and measure the volume, measure the mass of the graduated cylinder with the water. Boom, boom, boom. When you're writing out the procedure, you want to make it simple, direct, and something that you can repeat. So with that being said, I lost my participants list. Let me take a look at that again. Are there any questions about what I just said about that? That is to say, the procedure. Okay. Now I said that we were, go ahead, Izzy.
Okay, so it says mass your graduated cylinder while it is empty and dry. Like take the mass of
Yes.
it
Yep.
and and also how are we to take the mass of it with
With your scale that I'm hoping you've bought by now.
I did the little one.
Yeah.
Does it go up to that it seems kind of heavy like the graduated cylinder
Well, that's a great question, Izzy. Let's check it out and find out. Okay.
because it's glass. I had a feeling like it only measured up to a certain
Right. And it turns out that this guy measures up to 300 grams. 300 grams is almost, it's a little more than half a pound. So the question is does this graduated cylinder weigh more than half a pound? Because if it does, we will max out our scale, but let's find out. So my graduated cylinder is also made out of glass. You can hear me tapping it on the tabletop. I'm going to turn on my balance and I'm going to switch the screen around here real quick. So you should be able to see the number and my balance and my graduated cylinder. I'm going to turn it on. And you can barely see the numbers there. Part of that is because I have the light on so you can see my face. Let me turn that off. That's no help. But at any rate, I'm going to put the graduated cylinder on there. And it reads a mass, I can tell you it's 125.86. And this graduated cylinder can measure up to 300 grams. So this is about 126 grams. Every milliliter of water is about 1 gram. So if we put 40 milliliters in there, that would be about 40 grams, and the total mass would be about 166. So your balance should be able to handle the graduated cylinder and the water. I mean, it's a good question, but I think we're covered. Okay. We good? We good there, Izzy?
yeah, I'm good. I guess in my head I felt like it was heavy.
Yeah. Well, you know, when you have such a, what I would dare say is such a cute little balance, you know, this is something you would expect your neighborhood drug dealer to run around with. You think that, well, you're only going to put little tiny joints on here or cocaine or something like that. But in fact, this is a pretty stout balance that you could use for measuring portions for cooking. So, you know, if you had to add 100 grams of broccoli to a recipe, you could actually put this little thing here, and I guarantee you are going to have trouble putting 100 grams of broccoli in here, but you could do that. So that's what I like about this balance is it's so has such a wide range, but yet it's inexpensive. It's really cool. Okay, so back to the captain here. Let's see now. So you can see the, well, you can't see because I need to go back to my browser share so you can see what I'm looking at now. So you can see that the procedure I've written, you can whittle down to something smaller so it's quicker to write in your lab notebook. You'll notice for the data, it's pretty straightforward in this case. We're going to write out the data that we collect. Notice for the pennies, we're going to get the volume by displacement and we're going to get the volume by geometric shape. So we're writing down the initial volume of the graduated cylinder. So here's my graduated cylinder. We're going to put water in here, dump a bunch of pennies in, and then measure the volume again. So before and after. That's data. When you take the final volume and subtract it from the initial volume to get the volume of the pennies, that's a result. So we're not going to write that here in the data section. We'll write that in the results section. And then here we have a number of calculations. Calculate the mass of water and the density of water. We're going to come back to this section so you can see the kinds of things I'm looking for in this section. I know I'm kind of running around a bit, and I want you to remember about 50 hours ago, I said, and so for the introduction, we're going to move forward and kind of see the rest of this to help us write the introduction. So you can see we're calculating the density of the pennies using mass and displacement volume, mass and geometric volume, so forth and so on. And then the results, we make a table. And for the discussion, we discuss our results. And it says, discuss the results of the lab. It should start with the density of the pennies and the density of dimes was determined to be blank respectively. Comparing these with the densities of copper and zinc, this indicates that pennies are mostly copper and dimes are mostly zinc, if that's what it indicates. Or it might be, it indicates that pennies are mostly zinc and dimes are mostly copper. And if your original hypothesis is that pennies are copper and dimes are zinc, you'd say, well, then our original hypothesis was false. And then you might describe reasons for that. So that's how the discussion is going to go. And that's also going to help us to inform what we're going to write in the introduction. All right, so now let's start talking about the introduction. I like to make the introduction bullet points. And the first thing I'd start off with is density is mass divided by volume. And then I'd go on and say mass is measured with a scale and volume is measured by volume displacement or by geometric shape. And then I would go on to say that we're going to use this property of density to determine what pennies are made out of and what dimes are made out of. We will experimentally determine the density of pennies. We will experimentally determine the density of dimes, and we will look at those densities and compare them to the metals copper and zinc to see if pennies are indeed made out of copper because they look like they're copper, and if indeed dimes are made out of zinc because they look silvery like zinc. So that could be your introduction, as simple as that. And you can make bullet points out of that. So your first bullet, density is mass divided by volume. Next bullet, mass is determined with a scale. Next bullet, volume is determined by volume displacement or by geometric shape. And then the next bullet point could be pennies look like they're copper, dimes look like they're zinc. So the density experimentally determined will be compared with the real density of copper and zinc to see what pennies are made out of and what dimes are made out of. And you're done with your intro. Some intros are longer than that, but this one can be pretty short. Does anyone have any questions about what you might put in the introduction here? Great, so we're going to move on. The next section is safety. And if you read through this whole lab, you won't find a darn thing about safety. But if you read the procedure, it says use a graduated cylinder, use a penny, use water. So in my mind, there are no safety issues because you're using things that are harmless. Water, pennies, dimes, graduated cylinder, or balance. So that doesn't mean you don't leave the safety section off, or excuse me, that means you don't have a safety section. It means you do have a safety section, but you're right. There are no safety issues for this lab. And that's it. Any questions about safety? Okay, we'll move on. The procedure we talked about, you can make bullet points about that. The data, I described to you the data you should probably have. And let's now look at the calculations based on the assignment. So you're going to do these calculations here where it says do all these calculations. And you're also going to include calculations from the assignment that are calculations. So let's go down to the assignment. So quickly look at question 1. Are there any calculations there? What calculation is there, Izzy?
Um, converting the densities.
Actually, number one just says a student puts the pennies in a Ziploc baggie, shoves them in the water, and measures the volume. Is the volume going to be too large or too small? So we're not really measuring anything, but we're thinking about, well, what if you stuck a plastic baggie in there with your pennies? What would happen to the final volume you'd measure? And my answer is, well, the baggie has volume, so the volume would be higher. Are you with me there? So there's no real number to go with this or calculation. You would simply say, you know what, the volume would be too high. Why? Because the bag has volume. Let's look at number two. How will the Ziploc baggie displacement volume affect the density? Well, in this case, write down on a piece of paper, density is equal to M over V. With number one, we said, hey, the volume will be too large. Take a look at that formula. If we put a V in there that's too large, how does that affect D? So let's say V was supposed to be 2. And when we measure it, it's 10. How does that affect the density? Who wants to try that one? No one's game? So let me show you.
Can you repeat it?
Pardon me?
Can you repeat it?
Yeah, so let's say that you calculate the density of the pennies and you don't use the plastic baggie. And then you calculate the density of the pennies and you do use the plastic baggie. How will the density of the pennies when you don't use the plastic baggie compared to the density of the pennies when you do use the plastic baggie?
The density would be less if you use the baggie because density is mass over volume. So larger volume would make a smaller number.
Exactly, because the volume is on the bottom. If you have too big of a number, it'll make the density overall smaller. Perfect answer. So those are the kinds of answers I'm expecting. You would say, well, the density would be too small. Explain. Well, density is, we would say, inversely proportional to volume. Since the volume is too large, the density would be too small. And then I asked some other questions. 3 and 4, there's no real calculation. 5, no calculation. 6, no calculation. But 7 does have a calculation. Convert the density. So you should put that into your calculation section. If you look at 8, no calculation. 9 does have a calculation. In fact, it says calculate your percent error. And 10 has a calculation. So you want to put those calculations into your calculation section. But the rest of these, you're not going to put into the calculation section. So let's look at number 10, and let's say you do that calculation, and it's in the calculation section. What I would do for my assignment, I would say, look at the calculation section for this answer. That way I don't have to write down the calculation twice. Any questions there? Okay, so I'm not trying to make you repeat a lot of work. I'm just trying to make you be able to do all this work and point to it in your lab somewhere. Okay, so now that we've looked at the assignment, let's go to some of these calculations. So what we're going to look here is at these calculations, and I'm going to switch screens to my paper so you can see what I'm writing. We'll take a look at calculate the volume of 1 penny by water displacement, or the pennies by water displacement. Calculate the volume of 1 penny by geometric dimension. And we'll take a look at that. Oh, I didn't put anywhere in here to Well, I guess I do have that. Get the mass of the 50 dimes. I do have to change something up here. Get the density of 1 penny, or get the mass of 1 penny and get the mass of 1 dime. I see that now. So I'm going to do a switch screen so you can see what I'm writing on paper. Okay. So let's look at the penny, the calculations for the penny. So let's say that we have the mass is 2.5 grams. You can do better than that with a balance that I suggested you buy. Let's say that the volume final is, well, actually, the mass of 1 penny is 2.5 grams, and the mass of 50 pennies is 125.1 grams. So the volume final for the 50 pennies, let's call it 44.1 milliliters. And the volume initial, let's call it, I don't know, 5.2 milliliters. You'll notice for the graduated cylinder here, if I zoom in on it, so bear with me here. You can see that if this is 50 and this is 60, that there are 10 equal spaces between 50 and 60, which means each space is 1 milliliter. So based on what we learned in the previous lab, if each smallest division is 1 milliliter, we can measure to 1/10 of a milliliter. So that's why my values that I've written down here, and I'm going to zoom back out now. That's why my values are recorded to the 1/10 of a milliliter. So this is just the data that we have. And here's what you would show for the calculations. So, oh, and I'm sorry, let's also get the diameter. I'm just going to call it 1.5 centimeters. This is not the appropriate precision for your ruler. You should be able to do better than that. And let's call the height of the penny 0.1 centimeters, and you can do better than that. So for the calculations for the penny, volume by displacement, we would have V final minus V initial, which in this case would be 44.1 milliliters minus 5.2 milliliters, which would end up being 38.9 milliliters. Volume by geometric shape, we would do the following. Now, I'm going to show you the formula for getting the volume of a penny. So a penny looks like this, and this is the diameter. And if I draw the penny from the side, kind of from the side, it looks like this. And this circle here is the area of the penny. And here's the same circle looking at my image from the side. This distance right here is the thickness of the penny, but we could also call it the height. I would call this shape a disc, like a frisbee or a frisbee disc if you play disc golf. But this is also the same as this shape here. It's just not as tall. I don't know where cylinder becomes disc and where disc becomes cylinder. But regardless, this here could be called the thickness or the height. So there's a joke in here. When you're a young person like I used to be, I was so skinny that I was the guy who would plug things in behind the piano because the piano was too large to move. So you needed a skinny person to plug things in behind the piano. That was me. And so, you know, we always talked about how tall I was or what was my height. As I've gotten older, I've begun to look more like my dad when he was older. And so I'm a little rounder. And I'm approaching the time in my life when you don't ask how tall I am, you ask, how thick is he? So that's a joke. It's okay to clap your hands. No claps? Okay, so I'll stick to my day job, teaching chemistry. All right, so to get the volume by geometry, you take the area and multiply it by the height. What is the area of a circle? It's pi r squared, height. Now, this formula here means that we would have to take half of this diameter and plug it in here. And I'm going to change this to 1.6 centimeters because it's going to show you how easy it is to make a mistake. A person might do this. Does everyone know what half of 1.6 is? 0.8 centimeters, right? And let's call this 0.11. Now, when you calculate the volume of this, you would probably end up with one significant figure because of this 0.8 only has one significant figure. And that would be wrong. And that's because you should actually be doing this. The radius is the diameter divided by 2, which is 1.6 centimeters divided by 2, which is 0.80 centimeters. This has 2 zig figs, so this should have 2 significant figures. And then plug that in here. So in general, I don't like doing this and then doing this and plugging that number in here. I'd just rather not do that. So here's what I do. The volume definitely is pi r squared h. And this is on a piece of scrap paper. So that's pi parentheses r squared h. This is the same thing as above. And since the radius is diameter divided by 2, I'm going to put pi diameter divided by 2 squared h. And then I get pi d squared h over 4. So here's what I would actually use, because that way I can use the number I get for the diameter directly and not have to half it. Regardless of which way you do it, you should get the same answer. Any questions there about calculating the volume of the penny based on its geometry? Any questions on that? Okay, good. All right, so I'm going to change my share back to the lab itself so we can look at it. So that shows you the calculations you would make for the penny for volume. And then you would also calculate the density. So you'd put, for the density, I got to go back and do another share now. For the density, you would have the density of the penny using the volume by displacement. And that would be the mass of the penny divided by the volume by displacement. And you'd plug 2 numbers in here. And you would also calculate the volume of the penny by geometric shape. And that would be the mass divided by the volume for geometric shape. Hopefully, when we calculate these 2 values, they will be similar. Because density is a intensive property. It doesn't depend on how much you have. So therefore, the density of 50 pennies by displacement should be the same as the density of 1 penny by geometric shape. So these densities should be the same because density is intensive. It's an inside property. It doesn't depend on how much you have. Any questions here on the two calculations you should have for the density of the penny? No questions? Okay. And you're going to do the same type of thing for the dime. You're going to do the volume by displacement, the volume by geometric shape, and the density by displacement and the density by geometric shape. Now you'll notice in the, and I'm going to go back to the lab. Sorry for the jumping back and forth, but if I don't show you what I'm talking about, it'll not make much sense. But do you take a look here at some of these questions? Why are 50 pennies used for water displacement? Why do we only need one for geometric shape? Which method do we expect to be more accurate and why? Those are things for you to think about. I'm not going to give you the answer here and now. I want you to think about those things. Let's look up at number 6. It says, look up the densities of copper and zinc using webelements.com and report the values. So let's take a look at that, okay? So I'm going to go to webelements.com. This is a chemist's favorite website. And here you can see we have copper. And can you see this little speaker here? I'm going to go ahead and play that, and we're going to listen to this.
Element 29, copper, is one of the most important metals. Copper is reddish with a bright metallic luster. It is malleable and ductile. It is a good conductor of heat and second only to silver in electrical conductivity. Its alloys, brass and bronze, are very important. Monal and gunmetals also contain copper. Apparently, the reason that policemen in the USA are nicknamed cops or coppers is to do with their uniforms, which used to have copper buttons. The most important compounds are the oxide and the sulfate, sometimes known as blue vitriol. Copper reagents, such as Fehling solution, are used in analytical chemistry in tests for sugar.
So you get a little bit of some background about copper. You know, you find that little interesting thing. Oh, that's why we call them cops, because they had copper buttons. That's kind of interesting. So if we scroll down, can you see we have physical properties here? I'm going to zoom in on this. So I'm going to write that down, that the density of copper is 8920 kilograms meters to the -3. I'm going to zoom back out. And we're getting the volume in centimeters cubed or milliliters. And we're getting the mass in grams, not kilograms. So how are we going to use this number? Well, let's take a look and look at the lab. I actually asked you in number 7 to convert the densities found on Web Elements from kilograms meters to the -3 to grams centimeters to the -3. That is from kilograms per meter cubed to grams per centimeter cubed. So I want to show you a few things here. And I'm going to switch my share so that you can see what I'm writing. So this is the value that we found at webelements.com. And this is the same as 8920 kilograms over meters cubed. And I'm going to prove that to you. So we know that any number or any value divided by 1 is the same value. So I'm going to put this over 1. And then I'm going to multiply by something that's equal to 1. And I'm going to multiply by meters cubed over meters cubed, which is equal to 1. So I have this number that I've divided by 1, so it doesn't change. I'm going to multiply it by meters cubed over meters cubed, which is 1, so I'm not changing the amount. And what happens here is that this meters to the -3 and this meters to the 3 becomes meters to the 0 power. Meters to the 0 power is 1. So these essentially cancel. This on the bottom, however, does not cancel, and meters cubed times 1 is meters cubed. So I've just proved to you that this is the same as this. And now that you know that, you can now use the trick. Since this is over 1, the trick is cross the line, change the sign. So I'm going to take this meter to the -3 and cross the line. This line here is called the vinculum. And if you memorize that one thing, that the dividing line is called the vinculum, you will know something that your math teacher does not know, because they don't know it's the vinculum. And when I tell them that, they go, oh, I never knew that. Because for years I would ask the math instructors, what do you call the dividing line? And they say, I don't know, the dividing line. So after years of careful research, I finally figured out what that dividing line is called. And I didn't really do years of careful research. I found it on a Snapple cap, inside of a Snapple cap. Funniest thing in the world. Snapple has all the answers. It's like the Hitchhiker's Guide to the Galaxy. Okay, so when you cross the line, you change the sign. So instead of meters to the -3, it's meters to the +3. Any questions about cross the line, change the sign? Now, this is the way you'll see physicists write that value, because they don't like denominators. I think they only like numerators. Me, I like denominators so that I can see what things cancel. It's a lot easier to do that than do this times this. All right, so we want to take this 8920 kilograms per meter cubed. We want to take the top and turn that into grams. And we want to take the bottom and turn that into centimeter cubed. And if you recall, we've done some problems like this in previous sessions, where on the bottom, we can use 100 centimeters is equal to 1 meter, but we have to use it 3 times. So you're going to use this to calculate the grams per centimeter cubed, and then you compare it to the value that you have, or you determined experimentally. Any questions there? You're going to do the same thing for zinc. You're going to look up the given density of zinc in Web Elements and convert it to grams per centimeter cubed. That's another calculation where you're going to put that in the calculation section. And in the assignment, you're going to say, oh, just look at the calculation section. Any questions about that? Okay. So that being said, that's pretty much the entirety of the lab. We talked about safety, procedure, data, calculations, results, and discussion. So now I'm going to open up the floor to you. Do you have any questions about what we just talked about? If you do, just unmic yourself and ask away. Okay, that being said, do you have any? Oh, there's an unmiking. Melissa, go ahead, please.
I just have a question about the other lab, the measurements one. So
that's what I was just going to open it up to that also. So go for it.
Okay. In general, do you mind if we skip pages for neatness? I have a problem writing on the backs of pages. It turns all scribbly.
I don't, Melissa. Let me actually tell you what I like to do with a lab notebook. So here's the lab notebook kind of opened up. And this is going to be the title. This is going to be the intro. This is going to be safety and so forth. And on this page, I put notes. And so I put all sorts of scribbles here in pen. And it's just notes to help me understand this side. And then when you open up the next page, it's the same thing. On the left, notes, and on the right, I have my nice, neat lab. Now, if you're doing something like that, that's the way I would do it, but it's okay for you to have spaces in here that say notes and then have stuff written down. The way I've drawn this, it looks bad. You're not allowed to tape pages in and have it extend past, but you could have a page that looks like this. Here's your title. Here's your intro. Here's your safety. And then maybe you have some notes here. And maybe you kind of set that aside by doing that. And then on the next page, you might take up again with procedure. So I'm not sure if this is kind of what you're talking about, Melissa, but that's fine.
Yep, that answered my question.
What I would ask you to do though, Melissa, is that for that part of your lab that is notes, I'd write notes. And here's what's going to happen if you happen to send that into me, I'm not going to look at it. And it's not going to be part of your graded lab. Fair enough?
Yep, that works. I also have follow-up questions if you're ready for the next.
I am.
So in the measurements lab, the procedure list didn't include calculations and conversions from the assignment part. Do I need to add that in or just make that part of the assignment only?
I think if let me go back to the share of my browser. And what I'm going to do here is I'm going to go back to the modules. Hopefully module 0 will collapse. There it goes. And if we go to measurements, I'll open that one up. Okay, so the calculations here say based on the assignment. So if we drop down to the assignment, do you see how number 1 is a calculation?
Sure. And
I'd put that in my calculation section.
okay.
And in my assignment, I'd say refer to the calculation section.
Okay, yeah, I did that for all the calculations in the assignment, but the procedure steps don't actually say anything about doing any of those conversions. So I didn't know if I needed to add
No.
more steps in.
The procedure is not what you're doing with the data you collect. The procedure is actually how to collect the data. So I think that's a distinction you're kind of asking about, and I've never really thought about making that distinction. But procedure is data you collect and how you collect it. And the
Okay.
calculations are more about, well, what you do with those, with that data. So
Okay.
I've never really thought of making the calculations part of the procedure.
Okay, so then basically you take what you've done in the assignment and you use that to make your discussion out of?
Well, that's a great point. In your calculations that you put and in your assignment, I'm trying to make you think about things that you want to put in your discussion. So for instance, one of the questions in the next lab, the density lab, is which do you think is going to be more accurate? Getting the density where you have the volume by displacement, or the density where you have the volume by geometric shape? And my argument would be displacement's going to be better because you have 50 of those things, not just one. Plus, when you look at a penny and we calculate its volume based on its height and its diameter, we're assuming that the thing is perfectly flat on top. No ridges, no bumps, no weirdness, because all of that will change the volume. So if you look at the edge of a penny, is it as thick as the rest of the penny, or is it thicker than the rest of the penny? So all of that might have an impact on the volume, and I don't know whether or not you're getting a real good volume with that. In addition, when you're measuring the edge of the penny with your ruler, how precise can you be and how accurate can you be? I think it will be a challenge. So in my opinion, getting the density by displacement is probably going to be more accurate. And so in my discussion, I would write stuff like that. And then I would say, so therefore, I think the density of the penny is this number based on displacement. Does
Okay.
that make any sense? So those are the types of things that with the assignment, I'm also trying to help you with the discussion and things to think about.
Okay.
So
I think Izzy has a question.
yeah, I see that. Izzy, go ahead.
I just wanted to verify that the density lab is going to be due this Friday.
Now
Because
I'm
you
going to
mentioned
change.
you might
I'm going to
change it.
change that, but you're also going to have a lab on Thursday. And Thursday's lab is not going to be one where you do an experiment. It's going to be about scientific method and whether or not you should believe scientists.
I also had a question about the quiz on Friday. Is it going to be covering all the materials from chapter 1 and the conversions, or is it just going to, or is it a quiz on the conversions?
It's all of chapter 1. So
Okay.
it'll be mass, it'll be mixtures, chemical
What
properties.
about the elements? Because I know you mentioned we don't have to memorize them yet, but I know some of the questions were on like the elements and just.
You need to know the elements. And did you ever see a session where I listed the elements you should know?
Yeah, you mentioned that we have to know the first 40 and then the additional ones as well. I listed them,
Yeah.
but
And the additional ones were common ones, at least what I consider to be common ones, like plutonium, uranium, americium, but not uncommon ones like protactinium and erbium and things like that.
and that's for this Friday.
Yeah, you should know
And
those names and those symbols. Flashcards are the way to go.
all right.
For the
Sounds
first
good.
40, you probably know 30 of them already.
Yeah.
And so that's just an additional 10. And for the other ones, they're not that bad. Once you start getting used to gold being AU, you can make a game out of it. You can say AU. And I'll go, why are you saying AU? Because you're gold, man. Right?
That's pretty good.
So when you start saying AU to someone, you tell them, no, I'm calling you gold.
It's not
All
rude.
right. So the other ones aren't going to be too bad. There are some tricky ones like radon and radium. They both start with RA, and one is RA and one is RN. But you learn tricks, like for instance, radium doesn't have an N, so its symbol cannot be RN. So you'll quickly give yourself some tricks. And for the ones that you don't know, make flashcards. And I've always found that with simple things like that, if you have 20 of them and you make 20 flashcards, that alone will take you about 5 minutes because you make your flashcards very simple. Symbol one side, name on the other. 20 flashcards, 5 minutes, no problem. To learn all 20 is going to take you about 3 minutes because you're going to go through the 20 flashcards fairly quickly. You set the ones to the side that you already know, and you focus on the ones you don't know. As soon as you know them, put them to the side. And soon your pile gets to be very small. You shuffle them all back together, go through all 20. You find out that you forgot just a couple, and you pick those up, go through the cards again, and it's very quick. This is how I aced zoology. I made flashcards for everything. And I ended up with like a couple thousand flashcards. And when you make flashcards like that and you go through them repetitively, you can go through like 3 flashcards or at least 1 flashcard a second, 60 flashcards in a minute, 600 flashcards in 10 minutes. It's a fantastic way to learn things and to develop your recall. So I'd use flashcards, Izzy. All right.
Yeah, sounds good. Thank you.
Okay, Melissa, did you have a follow-up on the measurements lab?
Just one more on
Sure.
the, sorry, I'm trying to find it again. I went to a new tab. On the assignment portion in 8 and 9, it says to use the conversion from the store product or the beverage container, and then compare the two results. What exactly does that mean, and what do you want written in the book?
So convert the mass of the store ruler to ounces using the above conversions and using what you found from your store product, right? Number 8.
Yeah.
So what I want you to find out there is that when you convert the mass of your store ruler to ounces, you're going to get a certain number. And when you using 454 grams is 1 pound and 1 pound is 16 ounces, you're going to get a particular answer. When you use the store product, you're going to get another particular answer. And when I ask you to compare the two, you should find out that they're very, very close together. So let's take a look at an example, okay? So I'm going to change my share screen. So let's say the ruler weighs 1.56 grams. And we're going to convert this into ounces. So that would be 1 pound, 454 grams. And then 16 ounces and 1 pound. And if we work this out, let's see what we get. 1.56. Now you can see I clearly invented this number up. I don't know how much your ruler weighs. So I get 0.00, and since this has 3 significant figures, 344 ounces. This is defined, so we've got infinity significant figures here and here. This one has infinity sig figures, and this has 3, and this has 3, so we end up with 3 significant figures. Now I'm going to ask you to wait for just a moment here. Okay, so here I have this Idahoan buttery home style mashed potatoes. We've had this on our shelf for about 3 or 4 years because it looks horrible. But you see the 4 ounces and the 113.4 grams. So I'm going to take my 1.56 grams, multiply by 113.4 grams. Oops, got to cross that out. 1.56 grams, and I'm going to multiply by 4 ounces over 113.4 grams. Now, this is one of the things that is always hinky about using a food product is that looks like 1 zig fig. But in fact, we should be treating that as infinity and that as 4. So let's do this calculation. Wow, I get something completely different than that one. And I get 0.0550 ounces. Now, let me make sure I did this calculation correctly. Oh, I didn't do this calculation correctly, my friends. I pushed the wrong buttons. And this is the problem that I have, is if there's a way to screw something up, I'm going to figure out how to do it. Normally, when I do a problem like this, I estimate the answer before I move on. That way I know my answer is going to be correct over here. And this is what I get when I redo the calculation. So take a look at these two numbers using different conversion factors. This one, ones that are defined or measured pretty well, and this one off of a food product. So I'm going to go back to my that question that we were just looking at, Melissa. And you'll notice that one of the questions is compare the two results. So I'm going to say, well, gosh darn, I get the same answer either way. Does that make any sense?
Yep, that was perfect.
And, that's all I'm asking you to do is, I kind of want you to realize that conversion factors are everywhere. You're surrounded by them. And in fact, when you go to a grocery store, chances are, just because we were together here now and we saw this, you might be looking at another product you pull off the shelf and go, oh, look, there's another conversion factor. Oh, there's another conversion factor. You might not be able to get away from it unless you're a normal person, in which case you'll be okay. But if you're one of those persons who finds out something new and you get involved with it, you're going to be seeing conversion factors everywhere.
Sounds
Okay,
like
so that was the purpose there, to see that, to show you that, while we do measure certain conversion factors, you don't need to measure the same one, memorize the same ones. You memorize the ones that are most useful to you. Okay, so that's pretty good. Now, normally I like to finish around 7. My evening sessions are a little shorter than my day sessions. We went a little long tonight. I will tell you this, that in the morning sessions today, we did some additional problems from the end of chapter 1. Problems like 18, 20, 22, things like that. So you might want to play some of those earlier videos from this afternoon or morning and scroll to the end of the video until we start doing problems at the end of the chapter, because there's some good stuff in there. Tomorrow, when I have the sessions, we'll be picking up from where we had left off and continuing with more problems where we're doing a lot of conversions and a lot of calculations and figuring out how many significant figures we're supposed to have and so forth and so on, using dimensions to decide what goes on top and what goes on the bottom when we cancel things. All right?
Sounds good.
Does anyone have any other questions?
No, I think my trickiest part is just those the conversions that are cubed or like squared, and I think those conversions. But I think, I mean, when we use your method, when we multiply it multiple times, it does simplify it. I just feel like in the textbook, it kind of does a different way, and there's like so many different ways of doing conversions, and I think that's what kind of like makes me feel like, oh, should I be doing it this way or that way? Like,
the way you should be doing it is the way that makes sense to you, but also shows the sense it does make to you, so that a person could follow it and understand it. So when I show it to you, it makes sense because you can see things canceling. And when the book shows it to you, it should make sense because things are canceling. So in that way, they both are good, but there's a slight little difference for each person. It's kind of like dismounting a bike. Some people, they stop the bike and they swing their leg over the back of the bike. And some people who are more limber than I am, they'll stop the bike and flip their front leg over the front of the bike. And I don't do that because I've fallen down too many times. But both methods work, but you probably have a preferred method. And some of us dismount the bike by crashing because we don't know how to ride a bike very well. I don't prefer that method. All right, so now that we've reached the end of our session here, what I'm going to ask you to do is turn on your mics and say goodbye to everybody.
bye. Have a good evening.
Goodbye, everybody. Thank you for attending. I appreciate it. And how do I stop this?